Thanks everybody for coming. I know it's like late in the afternoon and hopefully you're all over your carbo crash from all the sandwiches at lunch. I'm Bryce Kerley. I'm going to talk about MapReduce and the React key value database you can use it with. I work for Basho, the company that makes React, so like this was an important thing for me to learn because I just left there a week ago.
Really?
So,
Are you local?
Miami.
Miami?
Yeah. So one of the big problems facing computing is that you just can't buy a faster CPU. You can get like 3 gigahertz, and that's it. You can get a lot more CPUs for less money. You get more CPUs that take less power, but they're still sort of at this kind of speed cap. So what you need to do to be able to make use of all these cores to make your algorithms run faster is to pick a distributed algorithm. So some kind of algorithm that can be run in multiple places at the same time and speed up linearly. A good example is password cracking. So if you break into, or if somebody gives you a database legally that's full of password hashes, you could use a parallel computer like a video card or rent like 100 video cards at Amazon for like $6 an hour and crack passwords on those really frighteningly quickly. So pick like long 50-character password and use software to run this. So your database sucks. Whatever you're using, it's not very good. If you're using a SQL database, they're very consistent. They keep your data. They make sure that everybody sees the data in the same way. But it's hard to make them distributed. So they usually either have like a single point of failure or they're a bit slow. If you're using a NoSQL, they sometimes don't have a single point of failure, but that means that the consistency kind of sucks on them. And it turns out this is because of the cap theorem. So there's consistency where everybody sees the same data, availability where it's always there, and partition tolerance where if parts of it can't talk to each other anymore, it still works. You get to pick 2. SQL picks consistency and depending on which one you're using, either availability or partition tolerance. A lot of the key value stores care less about consistency. They say, oh, it'll get there eventually. And I'm talking about React right now. React is available because it's distributed and no node is the master node. They just all talk to each other. And it's partition tolerant. The caveat is that when you're in a partition and 2 nodes on separate sides of the partition get written to, they might know different things. And whenever they get reconnected, now there's 2 values for that key. And your software has to deal with that somehow, either by picking the last write or merging the write somehow. So this, if you have to pick 2 of the 3 of these, what do? You use multiple databases. So GitHub uses like 3 different kinds of database. They use the Git document database to store all the source code. I think they use Postgres for the really relational stuff like users relating to projects and organizations. And they use Redis for a lot of internal stuff for caching, for queuing, etc. So as an example, if you're running accounting software, your ledger needs to be consistent. You can't, give people more money than you have. And you can't have more money than you have receipts for. So you're going to use SQL for that, and you're going to set it up with triggers and constraints to make sure it's consistent. On the other side, you have a site like Facebook, where you have status updates. If on like certain visits to Facebook, like half of your status updates are missing, and it's not consistent which half or what even constitutes a half, or if sometimes you go to Facebook and there's nothing at all there, you're going to go into Facebook. If you go to Facebook and your friends' like status updates from the last 30 seconds or 10 minutes don't show up, that's probably okay. So one last thing to be aware of is abstract distributed algorithms. So for specific tasks like hash cracking, there are specific distributed algorithms. For something less specific, there's really 2 distributed algorithms that you think about. And these are Google. I don't know if they invented these, but they invented sort of the way that they can be distributed across thousands of machines. The first one is map. Map is basically for every element in a collection. So if you have like an array of names or an array of words or an array of numbers, You do a transformation on them and you get a new array the same size with the transformed things. One example would be capitalize every letter in the sentence. You get a new sentence that is capitalize every, it's shouting, but it's still the same size and it's still a sentence. The other one is reduce. So for each object in the collection, you derive something from that object. It could be just as simple as like getting the numeric value of that object and add it to an accumulator or do something else with it. So at the end, you only have one instance. So the good example is if you have a list of numbers like in a spreadsheet, you would reduce those into a single number by adding them together or multiplying them or something like that. So MapReduce is a keystone feature of NoSQL databases, or as some people call them, key value stores. So how do you query a key value store? You write a distributed MapReduce function. React supports Erlang and JavaScript. You don't get to write SQL, so it's a little bit harder to query them. So one last thing about key value stores. This is a image I have in my Amazon S3 account. I forget why it just auto-completed. That is a bucket. So a bucket's basically a namespace for a key value store. With S3, a bucket is only owned by one entity. So I own Preston. Somebody else could buy Preston 1 or Preston 2. This is a key. It looks like a file name, but it's not actually a file name. It's and the big difference is that these don't have directories. So if I had like /images, /cars, /BMW, /that mess, that whole part would actually be the key, including the slashes and all. It doesn't have directories, they're just more characters in the name. And finally, this is the value. In this case, all the bytes that make up the JPEG image there. And React works the same way. It has buckets. Buckets are pretty much free. It has keys. Keys have a name that can contain anything, and a value that's just a bunch of bytes. Brief disclaimer, I don't work on React, but I work with people who make React, and it kind of signs my paychecks. So if I sound a little bit partial, please disregard it.
You guys just have a cat theorem guy too? Is that you?
It's not me personally, but
Oh,
we might
You're
have.
now working with the guy who eventually defined cat.
I think so. I haven't memorized the org chart yet. I haven't worked there very long.
That's pretty big.
Yeah.
All right.
So requesting a key in React is cheap. It's a constant time operation. But how do you grab more than one thing? Up until like 2 weeks from now, you MapReduce over it. And React MapReduce is a pipeline across multiple nodes. So if you have keys on node 1, some on node 2, and some on node 3, the map happens on whatever node the keys are on. And reduces happen first on each node where each set of keys live, and then a global reduce takes the output of those reductions and puts them into one big reduction. And that's automatic as long as you write your reduce function the right way. And I don't know how many people talked to me earlier today, but I was fighting with it for a while before I figured out all my mistakes. So I'm going to talk about how you would use this to find common trigrams from passwords. So there was a Bitcoin site that shall remain nameless that had their entire database leaked a couple months ago. And a bunch of people took, and it was like the worst community for a password leak to happen to, because Bitcoin is full of people who spend thousands of dollars on video cards for their processing ability to solve hashes in order to mine Bitcoins. These same video cards are amazing at cracking passwords, like the ones that not this site, but another very similar site had leaked. So there's a big file of passwords, of hashes floating out there, and now most of them have passwords next to them. So what are we going to do to find the trigrams from each of these passwords? The first step, and yeah, I didn't make a lot of slides for this, so I'm going to talk you through it, is I grab the password out of the database as part of the map function. I see how long it is, and I decide how many trigrams I can get out of it. So there's the number of trigrams in a word. In this case, there's one here, one here, one here, one here, and one here. So that's, and I made a math mistake, so yeah, that should be length minus 2. But so I know how many trigrams there are, and I iterate through the password, slicing off 3 of them, and pushing them into an array, basically. And I return an array of all the different trigrams I found. That goes on to the reduce step, which I basically brute forced and through coded this until it worked, especially after fixing a variable name problem, which was a little bit embarrassing. But basically I go through, and now I have all this list of trigrams, and I want to sum up how many times I see each one of them. Finally, once I wrote these 2 functions, I put them into a big pipeline like this, where I read the passwords bucket and take every password out of there, plug it into the map function from above, and from that it goes into the reduce function, and from that, that's the end of the pipeline, and it dumps those out to the request. So I'm going to try a live demo. So down here we have the JavaScript that's been mashed into unreadability, basically. And yeah, spoiler alert, it looks, here we go. So it just queried the database, where's my cursor? For all the trigrams. So K12 appears once, HEA appears twice, 234 appears 9, 123 appears 16 times, etc. So, and there's a lot of these. And if I had a bigger cluster of not just my notebook computer, I could have requested a lot more passwords in the same amount of time. If I went and blew a bunch of money on Amazon S3 machines, I could have done this analysis with like millions of passwords in a couple of minutes once I got the code written. And that's the live demo so far. No, those either screw up the slides or screw up the live demo. So thanks for your attention so far. I'm Bryce. This is my email, Twitter, and GitHub addresses. If you have any questions, ask them now or ask me later.
So is React, is it purely Kerley?
It's written in Erlang, so it works on Mac, Linux, Solaris, probably most Unices it works on, but I don't think anybody's tried it on Windows.
Why would they?
So what are some typical use cases for?
So the MapReduce stuff, and I just learned how to do this literally an hour ago. And it's going to be less popular from here on out, but so in the next version of React, they're bringing in secondary indices, so you can query things by values that aren't their name. But if you're migrating old data, it doesn't have indexes for those yet, so you'd use MapReduce to build the index, the first pass through, and then on commit in the future, you'd index the new stuff then.
So compared to something like Cassandra, this is the only interaction is through MapReduce? So if I want something out of the database, I have to provide a function.
If you don't know it's bucket and key, you use MapReduce today. In 2 weeks, you'll be able to use secondary indices and full text search.
Okay.
But I haven't learned those yet. But I suspect they're a lot easier and faster. What we see a lot of people using React for is like time domain stuff. So I have a Fitbit. It's a pedometer, and it basically says every day, it remembers how many miles I've walked, how many steps I've taken. So what I can do with this is the Fitbit website that this syncs to provides an API. And I can take stuff out of the Fitbit website and remember it each day inside React, and then use MapReduce to count how many steps I took in a given week, etc.
What's the data model like? Is it anything like Bigtable, or is it something completely different?
The way it's stored on disk is actually there's 3 different storage engines. There's one based on InnoDB.
Oh.
There's one called Bitcask that I read the paper for, but it was a kind of short paper. And there's one called LevelDB that I think Google released a little while ago.
Yeah. Yeah, I saw a presentation on Web Machine.
Okay.
That was very interesting.
Yeah, Sean, my coworker, is giving a presentation next week in New Orleans about Web Machine for Ruby.
That's very interesting stuff.
I haven't looked at it yet, so I'll take your word for it.
Yeah. It's on the info.
Okay.
Does React have any caching for things you keep MapReducing a lot? Or?
It doesn't, no.
Okay.
And the reason for that is it's not a big, the MapReduce thing for it sort of falls into a weird middle area where it doesn't do big MapReduce jobs like you use Hadoop for.
Right.
So you MapReduce for a smaller job or do it less frequently.
Okay.
But it generally doesn't do much, but what it does, it tries to be good at.
Okay.
So we talked about distributed processing.
Right.
Do you know if they're using it or if anybody is using that same approach for things like fluid mechanics and computational fluid dynamics or protein folding or any of that stuff?
And using React for that or using MapReduce for that?
Well, just the...
Okay. So from what I understand in a lot of the simulation stuff is it's a bit too slow or hefty, or there's a lot of stuff that you can do with simulations that doesn't map well to MapReduce.
Okay.
Pardon the phrasing there. It for like a lot of the protein folding, the reason it takes so long to do the protein folding is because there's a lot of relationships between everything. And mapping, like MapReduce, doesn't work with relationships super well.
So like computing, you were saying computing something, well, I'm sorry, that was a different talk. Computing one formula, let's say,
Right.
A plus B equals value. That doesn't really work
Yeah.
for this. But if you had, say, 100,000 elements that you needed to sum all of them, then MapReduce works
Right.
great.
Right. So MapReduce in general is for when you have a lot of stuff you need to do a handful of operations to. Whereas the protein folding or like finite element analysis
Yeah.
is a lot of stuff that all relates to each other.
Yeah, there's also time domain stuff, like the state of the adjacent cell 2 time indexes ago matters.
Right.
So that sounds like it would be a more complicated reduction step.
So would you use React in a real website like live, or would it be one of those cron jobs that happens and then just puts it somewhere that you just hook it and like?
I'd use it live.
Okay.
And this is part of the a longer discussion I had earlier today with somebody. But it really depends on the data that you have to deal with.
Right.
So if I was launching a website in the next 12 hours, I'd probably just use Postgres at first until I knew what people were doing with it and where the bottlenecks were.
Right.
And figure out a way to, if I needed a better data store to handle those.
Okay. No, but when you do have React as a data store that handles it, do you pre-compute the MapReduce and save the values as a cache, or is it okay that it runs fast enough?
If you're going to be hitting that MapReduce a lot, and I'm expecting the same result to show up a lot of the time,
Right.
I'd definitely cache it.
Ah.
But if it was being used mostly as a key value store and the
Right.
MapReduce was like a nightly analytics run or something.
Okay. Cool.
Yeah, I use Ruby MapReduce kind of style
Yeah.
for analytics all the time. I find it's really, really excellent
Yeah,
for that sort of stuff.
I use it in Ruby a lot, and I use it surprisingly a lot in like client-side JavaScript. Maybe because I'm a jerk, but
I find that the query times using a reducing function work so much faster. I can collect and aggregate you know, 500,000 records in,
Yeah.
you know, a quarter second.
And once you know how to write it, you get in the mode of thinking for it, which probably has been my problem today in that I haven't really worked with it in the React context before. Once you get in line for it, it feels really natural to do it.
Yeah, you gotta like reorganize your brain to think
Yeah.
differently. Like, well, yeah, that's challenging. Especially for procedural programmers who are not used to looking at like lots of sets, or lots of elements. And list programmers would probably be all over it, but
Yeah, it's
all three of them.
It's 4 now.
So in the
Closure these days.
8?
in the React that's coming out in a couple of weeks, so will there be indices? I mean, is that how it's
And
saying?
that's the secondary indices thing, which allows you to do map style queries faster.
Now, would you have to predefine those, or they're
Yeah.
automatic? Okay,
Yeah,
'cause
because
I know
they
Mongo and
have
some
to be
have.
created on whenever the data is committed to the database.
Okay.
Is it like how CouchDB will?
Right. Yeah, I was gonna tell DB has.
Where you sort of have your extra key values that come out of the map.
Yeah.
And then-
Yeah, and the reason for it with React is because React doesn't store objects or documents like Mongo and Couch do. It stores bytes.
Okay.
And so the standard that a lot of people use is putting JSON in there.
Right.
But there's no like hard and fast, you must put JSON in there. You can put whatever you want in there. And by custom, if it's structured data, it can be JSON. Any other questions?
Have you looked at,
At Basha, one of my friends, well, I was looking for contract work about 3 weeks ago. And one of my friends was like, well, we need a new full-time person doing Ruby and maybe Erlang. And like explaining this stuff to people, I'm like, okay.
cool.
And then I started 2 weeks ago.
Are they here?
They're distributed.
Ireland.
That works.
They're working from home.
Yeah. Yeah, so heavy traffic means the cat's sleeping in the doorway.
First time you shaved in a week.
I actually didn't shave this morning. But I usually shave just because I'm blonde and I don't want to look horrible for a month before a beard grows in.